So very good morning, everyone. Thank you for your interest and joining the webinar. Today, going to explore an important but often overlooked concept in structural analysis, that is torsion. Torsion, that is building's rotation about its vertical axis. So that is the response which is considered to be the weakest. And we have two topics in our presentation today. So, and our focus would be on presenting the features that are available in the ETABS to handle them. So the topics are the design eccentricity, which is for accounting the uncertainties in the design. And the other one is the dynamic characteristic of the building, which is the torsional mode. So often we find the torsional mode in the first mode in a model analysis, and how we can control it are the topics in today's presentation. Let us start with the part one of it, which is the design eccentricity. That means the inherent torsion, that is the offset of the center of mass and center of rigidity, that is always present in any structure. It could be for various reasons, masses, primarily the masses, and the stiffness does not coincide because of the configuration of the building itself, and then support conditions, etc. Now, this is inherent torsion. It is always there in the structure. You'll have to consider this. The other one is the additional torsion, that is the accidental torsion, accounts for uncertainties in the mass and the variability in live loads, which cannot be estimated. So whatever we have as a center of mass, which is based on an assumption as per the code. Wanted, we can also consider other variations, but typically, since we are following the code, we will use this mass estimation, and then the torsional component in a ground motion, which is not recorded, but can be accounted with the translation orthogonal excitation. Now, if you look at the code, we have the provision applicable for all buildings. That means you cannot avoid this. So it is a mandatory design consideration you'll have to do. And then we have the formula given in the code. And what is the design eccentricity considered in the analysis? So EDI is the design eccentricity, which consists of the inherent torsion, which is ESI, and accidental torsion. Our code gives 5% of the direction perpendicular to the application. Building width, 5% of it will be the accidental torsion. Typically, this is common for most codes, and this ratio varies between 5% to 10%. So accidental torsion, we are taking 5% here, and then the inherent torsion, ESI. Now let us see. A few things: the center of mass and center of rigidity tabs. Center of mass is calculated using this formulation. And then the center of rigidity obtained by applying unit force in X and Y and a rotation in the MZ, that is the vertical, about the vertical axis. Then you will get the centroid, center of rigidity coordinates. Center of mass for X is shown, Y is also the similar. That way you obtain this. Now in ETABS, these are pretty much automated. So we can straight away define the necessary definitions and start using the application of load and perform the analysis. So the very basic requirement would be the mass source. So mass source definition that you find under the define menu. Mass source is going to be the source of mass for all the lateral load analysis. So it can also give the seismic weight to the static equivalent static method. So in our presentation, we restrict ourselves to equivalent static method and response spectrum method. Start with the load patterns that we have to define these lateral loads. And you have this load pattern with auto lateral load option for the Indian code IS 1893. And it allows you to select the direction and eccentricity in the same load pattern, or you can also consider different load patterns for each of this. Get the analysis results separately. Even if you enable it in the same, you will get the output as step 1, step 2, and step 3. So 1, 2, 3 are these. It can also be used, but if you want the result separately as an output in the analysis case, then you can select one at a time. You can even combine the Y also if you want to do a quick X and Y combined. Program allows you to do it. Now we know the first one, which is the application of the story force. So when you define this, the program calculates the total base shear based on the other parameters and coefficients specified here, and that will be distributed as per the code force distribution along the height, quadratic distribution. So at any story, you'll see the quadratic distribution variation. When we consider the eccentricity, this is what the program does. It calculates the ETI using the same formula here, 1.5 times ESI plus 5% of the building width of that particular for the direction of application of loading perpendicular to that. So this is typically specified. Just enabling it, the default is sufficient. Note, for the negative direction, it uses the same 1.5 times ESI and 5%. This is because we typically, for the reversal of forces, we use the same earthquake load pattern in the negative direction. Right. And here is an example specifically made to show the differences visually that much. You can see the center of mass and center of rigidity. So it's intentionally made model so that the center of rigidity is very far from this center of mass. You can see, and we have 3 options available in the program. One is the auto lateral load. You can see the load pattern definition here. So let's say the EQX is type seismic, and auto lateral load based on the Indian code. Then other parameters we'll specify inside that, which I explained in the previous slide. So that is the default code-based load that will be applied as explained earlier. Next one is, in case you are calculating the lateral forces externally, the total base shear, as well as the distribution along the height to each story. If everything is not as per the Indian code, then you can use the user load option, which is also shown here in the same form. Type is seismic and user loads. And another extension of the auto lateral load is auto lateral load plus overrides. That means overrides for the eccentricities. So instead of the 5% standard for all the stories, for specific stories, you can override the eccentricity. So if you specify, let's say, third story, somewhat higher than the 5%, then you can specify the eccentricity directly, and program will use that eccentricity. So we have three options. And the situation here is like this. When put this center of mass shifted by that amount, and you can see from the original center of mass, this is shifted one for the positive, and this one is for the negative. This is when the force is applied from the left to right in the global X direction. Now, let us see it in some numbers, what program is actually doing. So we know that program can display the forces applied with the eccentricities. You would be seeing this kind of output in the display window, like what is the lateral force in each story, and along with that, moment. And what is this moment? This is the moment applied at the center of mass, actual center of mass, accounting for the shift or the eccentricity obtained for the design accidental torsion. Now, how that is calculated? Now, let us look at the second table, center of mass and rigidity for this building. You can see the center of mass and then center of rigidity for each story level. You can see I'm picking up only the first one, the roof level. You can see 0.24, that's why it is here in the y direction. So when you are applying the lateral force in the x direction, the shift is in the y direction for the center of mass, positive, and then negative. This is considering only the positive. And here I'm showing the manual calculation of the moment applied by the ETABS. And what it does is, it is the same formula, but the ESI, the inherent eccentricity, is deducted and the moment is calculated. 214. And the sign is negative here. That is to apply this moment. The positive shift. So the rotation will be like this about the z-axis clockwise. Clockwise moments are negative, anti-clockwise are positive. This is for the right-hand rule for the axis orientations. And for this joint, so negative moment is applied. So you can see the rotation. The arrow shows that for this positive. And this auto lateral load for the negative eccentricity. So it is the same set of forces, but this time it is positive. So we can see the center of mass in the negative shift. Case is the user lateral load. As I said earlier, for the comparison, I'm using the same set of forces to give the comparison of all the results, what we apply and what we get. And I assume the same set of base shear and force distribution in the story, and you can see the same I have defined. And this force is applied to the diaphragm at each story level, like this. With this is for the eccentricity, so it is going to have the MZ component. I'm showing only the negative ECC, the other one is positive, that is also there. But for comparison, I'm picking up only the negative eccentricity, and I've applied this force. And you will see for this load pattern, the loads are applied like this. It should be similar to the previous one. And then when you're using the overrides, so there is another load pattern which is showing that definition. And in the load pattern eccentricity, so when the eccentricity are specified by the user, so we will make this eccentricity ratio as 0, and then we enter into the override form by pressing this override button. And for each story, I kept the same eccentricity calculated like this. You can see it is the same 1.5 times of ESI plus % of building width, but deducting the current eccentricity. So this value we are providing here. Then here is a comparison of result of a particular node, the top roof level, this node, for all the 3 cases we considered. The default, which we can simply enable the eccentricity, and 5% is also default value, no change, and then specify it, and then you can see it is, so we expect this twist and the displacement in X direction. You can see 2.285, and for the user 2.285, and with the overrides 2.285. See, this is comparing only the negative highlighted, and you can also see the positive 8.7, 8.7, 8.7. Right. So depending on the situation and your need, you can use either of these options available to induce torsion for the design. Quickly show this model. This is the building. You can see these dots, which we'll cover in the next session. Come back to the presentation. So this is for the static, equivalent static method, or the static analysis. Next, we will switch to response spectrum analysis. How to specify the design eccentricity. That is an option when you define a load case for the response spectrum type. You can directly specify the eccentricity ratio, but it is a very simple way of doing it. But the actual or recommended way of doing it is by adjusting the mass location. So the procedure is depicted here with the flow chart. I hope to follow this, but I will explain it in the next slides. So basically, you need to shift the mass from the original mass position to a newer position where you want to consider the center of mass shift for the analysis. So it will be one shift for the positive and another shift for negative for one direction. So in the other direction, you'll have another left and right or the positive and negative shifts. So you'll have a series of analysis cases defined for the different mass sources. And mass is shifted, then you need to consider it in a nonlinear case because you're shifting the mass. So we have to define an empty nonlinear static load case. So this is to specify the shifted mass source. Let's say if it is a positive one, let's specify the positive one, and then there will be no other loads. And then you will use this as a starting stiffness for this new model case for this shifted mass. And then finally, you define a response spectrum case using the shifted mass model case. Although it will be much as it appears, but it's actually very simple. Let me explain it in the next slides. Now, here I'm adjusting the center of mass in a mass source. So we're considering only the x direction for the demonstration. So no y direction force and its variations for the eccentricity. So let's focus only on this. So the mass source 1 is the default one. We are using a copy of it and enabling this option, adjust diaphragm, lateral mass, move mass centroid by this ratio. This ratio is the EDI calculated earlier. That is 3.252, 3.25, something like that, and divided by the width of the building perpendicular to the load application, which is 12, and that is 0.27. And we'll apply the as a ratio here. This is for the positive, and similarly one for negative. Next, two load case definitions. One is for the mass shifted in the y direction. So we'll select the mass source, which is defined, and rest are all the same. The load case type is nonlinear static with the new mass source, and then blank, and then press OK. And then next one is model case using this shifted mass. Now you can see the model. I'm using Ritz here. It's okay. And then under the P delta nonlinear stiffness, right? Most cases it will be use preset P delta settings. That is from if any P delta settings are considered, that will be taken as the starting stiffness. But here we will specify this nonlinear case, which is this one. Right, and you can also see this mass source updated for this specified. It is the same model mass as previous. It's just a copy of it, and then we are updating it as a new case with these information. Then we have this final response spectrum case. the typical response spectrum case, but the model load case we just defined will be used here. These are all the same, but we specify the eccentricity as 0 as we have shifted the mass. For this case, it is positive, and just to show, so it is without eccentricity 7.1 mm, and then we have positive shift, so it has shifted by 9, and then with the negative, it has shifted only 6. So this is the median and positive and negative values. So that is how the response spectrum case utilize the shift and then perform the analysis based on the shift masks. Right. Now let's the part 2 of the presentation, which is the torsional mode. The previous one was for the design consideration. This one is for the characteristics of the building, the dynamic characteristics. So a torsionally flexible building is bound to show brittle damage or collapse under earthquake shaking. It's a known fact from the history. So that's the reason we avoid the torsional mode to be dominating in the initial modes. Now we have our code restrictions, and it gives some ratios where you can see the building is torsionally flexible or not, or within the range, and what else you can do. Whether you have to revise the configuration, that is here, it is more than 1.4 times average, which cannot be avoided. And then if it is within this range, and you can perform. And in that, the specification is that the building configuration shall be revised to ensure the natural period of the fundamental torsional mode of the oscillation shall be smaller than those of the first two translation modes along each of the principal plane directions. That means that with the mode 1 and 2 must be translational, can be torsional. Right. So the idea of controlling torsion isn't just about restricting the rotation. It's about ensuring every part of the structure moves together predictably and safely. So that's the idea and the goal. All right. Now, here is the case. For explaining the case, I would like to discuss a few things about the ETABS, and then we will move to this controlling of the torsional mode with some examples. So as we discussed earlier, the torsion occurs when the lateral load acts off center from the building center of mass or center of stiffness, right? The strategies what we have is only about the planning, keeping the building as symmetry as possible, and that the mass distribution is even, and also the stiffness distribution is even. Without that, there is no shortcut to avoid the torsional mode. Torsional stiffness can be improved only with a good lateral load resisting system like shear walls, bracings in steel structures, or sometimes the core walls to make it stiffer. And preferably, these are placed at the perimeter of the building. The reason is the distance or the radius of gyration. You can say that the radius of gyration of the mass and the radius of gyration of the stiffness, if that ratio is greater than 1, then the building is torsionally flexible. So less than 1 is, say, in simpler terms, for the practical purposes, we can say the time period. So T1, T2, T3 from the modal analysis. If the torsional mode's time period is less than 1, the ratio for the ratio of the torsional mode to the ratio of the translational mode, T theta divided by T translation. If that ratio is less than 1, then it is stiff enough. If it is greater than 1, then it is torsionally flexible. It means when mode 1 is torsional, then second or third mode in the denominator is always going to give you a ratio greater than 1, which is torsionally flexible buildings. So program gives you the model analysis results to investigate this behavior in detail. But we also have a few other tools we will discuss shortly. The strategies, other strategies, let's say this torsional mode checking and all would be suitable for small buildings or medium-rise buildings. What about high-rise buildings, where you cannot control everything with walls, stiffnesses through the bracings? So we need to do advanced analysis like time history analysis, and we'll be using tuned mass dampers to control the torsional excitation or the response of the structure. And in case of a very high seismic region, even for a short buildings, for example, a hospital building in a Himalayan region, then you cannot increase the strength. So in a highly seismic zone, so with a factor of 1.5 or 2 for the demand force as importance factor, then you will not be able to design such a building for these kind of torsional issues. So what we'll be doing, you'll be considering doing the building with base isolation, right? So why am I mentioning this? So these are the strategies, only ways to control the torsional mode, the weakest mode, and the program is very well capable of handling all types of analysis that are required for TMT or base isolation, or providing a real-time earthquake as an input and study the response of the structure. And you can also see the collapse mechanism um, with the nonlinear static, nonlinear dynamic analysis. So program is very well capable of it, but our restriction in today's presentation is limited to the linear static and the response spectrum. So I'm switching to next slide now, which is an example that shows a perfectly symmetric building, right? These are ideal cases. We'll try to see a couple of examples, but this is for understanding the torsion mode is dominating here. Now here it is a perfectly symmetric building. It's a perfectly square, so both directions perfectly symmetric, and then the core wall is at the center of the building. Your center of mass and center of rigidity coincide. It's a perfect expectation, yet torsional mode is fundamental, right? That is because the mass, I was talking about the radius of gyration of the mass and as well as stiffness. When the ratios of the masses are more, mass to the stiffness is more, you will get the torsion. So that's a simple, or in simple ways, you can compare the T, that is T1, T2, T3, and you can see the T1 is the torsional mode, which I'm finding it from here. R is at 83%, whereas UX, UY, it is 0. So 83% contributing in the first mode, leading to a torsional mode. That's what you're seeing. The masses away from here because the radius of gyration for this system is very small from the center of rigidity for these walls, and then the masses are much larger away from that, then that ratio becomes greater than 1, and you will see the torsional mode. And then later you'll find other outputs like simply seeing at the 1, 2, 3, the third mode, which is giving 70%. So 65% or 75%, 3 modes should be. So those things will be achieved, and even you will achieve this 90% modal mass participation in any analysis. Let's say you can see that's in the 6th mode, right? So that doesn't matter when your first mode is torsion. So you'll have to address this. So I've modified this structure. This is a sorted model, but using the same quantity of shear walls. So it is 6 plus 6 in each direction. So total 12 meters, and that is distributed in these locations. So moving away from the center of rigidity for the walls, primarily the walls are going to give the significant amount of lateral stiffness for the frames compared to the columns. So when it is very far, that is obviously we will be moving towards the corners. And although there will be practical reasons that we cannot provide at some corners because of the building aesthetics and architectural requirements, but the idea is that we take it very far from the center of rigidity. Note center of rigidity and mass again coincides, but the placement matters here. And with this, you will see the mode 3, 73, which is the torsional mode. And you can see the mode 1, I'm showing it here, just become translational for this case, right? Right, and you have achieved the 75, and then you have achieved 90% in mode 8, and we are considering anyway 12 modes, which is having 97% already. So this is a good model result that can be used for the response spectrum analysis. So whenever you are going to do a response spectrum analysis, you would be spending a good amount of time in this to control the torsion in the first 2 modes. It's very simple, yet you'll have to follow the basic principles. Take the resting elements away from the center of rigidity. Here it is. Now, if you would have noticed one thing, I've kept the symmetry. If you see the symmetry, about X and about Y both are symmetric. That's why CMCR coincides. But here I place the wall in the second span of this frame. Here in the first, right? For the X direction, it is in the last span. Y direction, this is. So this is 2. The weaker and stronger modes for the translation. I did it purposefully, but you can work. Obviously, it will be restricted by the architectural requirements and other things, right? Let's look at another output which is available in the ETABS program, which is the diaphragm force output. You can see this for the doubly symmetric building, right? You can see the response here. Yeah, I should. You open ETABS. So this is parallelly kept for the comparison, and you will see for this building, you will find this output under the display for stress diagram and diaphragm forces. The mode, and there is no load associated. It's a model analysis, so we can get only the resultants. That is what we needed. Let's enable the values, and then we'll see. Don't worry about the numbers, but just get the relationship between the magnitudes of these from the column nodes, and then the stiffer walls here. And you can see the direction, and the pattern itself tells you the torsional mode is going to be in the first mode, right? And once it is sorted, mode 1, doing the same, close these. And you can see mode 1, which is in the y direction translation as shown in the slides. And you can also see force in columns as well as the shear walls. And the arrow length is also proportional to that to give you the comparison. And this reactive force shows the uniform distribution of the stiffness in the structure, right? There are no weak or soft spots in the structure in this arrangement. Now, there is no substitute for this, but that's what I wanted to show you with this example. So it's a perfectly symmetric building. The another case is a common unsymmetric building like an L shape, T, or a recessed C shape, right? Where obviously the center of mass and the center of rigidity not coincide. And then you have the torsional mode as a fundamental mode. You will see that in the modal participating mass ratios. Here, you will see the coupling of translation and torsional modes will be happening. You can see 25% here and then 56% for the torsional, right? So it will be unavoidable, but that's how the response or the behavior for the mode shapes will find. This is mode 1, and then in mode 3 you have achieved 75% already. Then 8th mode 96, 97%. But this is not a usual behavior that you should design a building for. So what we did, I did only a couple of iterations quickly, and we have moved the same amount of shear walls, which was used as a core wall here. It doesn't mean that you should not use a core wall, but the distribution matters. You can still use the core wall, and then other distributed lateral load testing system. I removed the entire core system there and then distributed the same amount just to keep the quantity of shear walls the same and to show now the torsional mode has come in the third, and you can see. The other thing is the separation you can also see between the torsional mode and the translational mode. right? So the thumb rule is that every mode should, the primary structural modes should stay away from each other by significantly, as much as 10% at least in an ideal situation. But here we are achieving that with this distribution, right? Here it is dominant, has to be avoided. Here this is having is 0.28 divided by 0.36 is about 77 is the ratio. 0.77 is the ratio. That means it is more than 20%. So this is a well, but this coupling cannot be avoided, but this can be managed in a few more iterations. And then the similar comparison, the diaphragm force, you can see this arrow is a resultant force, so it is tilted, but that tilts a little sway to the left, but still predominantly in the y direction for the mode 1. There is one more example which I would like to show it directly on the ETABS program. So this is typical apartment building, high-rise building, and the element of walls looks okay, but still we are getting the torsional mode. This case, and although you need a couple of iterations to achieve this, the idea you can take away is that for these kind of buildings, apartment buildings, you can see by introducing this all walls at the corners wherever possible, architecturally as well, because without that it would be difficult. And I have introduced few corner L-shaped, and then I removed this vertical wall which forms the core, which is pulling the center of rigidity towards the right. So we removed it, and then this is done with brick infill, and then you can manage this is the staircase portion where you can have this vertical, and then I have reduced the vertical stiffness by removing, keeping it with the brick infill. Then you have output. This has become a translational. This one is first more torsional. Yeah. This is mode 2. The third mode is torsional. If we look at the table, center of mass and rigidity have come closer now. It's 27, 29, it's 27. And the center of rigidity here for the y direction is 27, 28. Just pretty close should be sufficient. Then you have modal participating mass ratio. Here, the torsional mode. Some coupling is expected because cannot make it so perfect. that only translation is available here in the first two modes. But this is significantly away from the translation modes, mode 3, compared to this one. Here, center of mass and rigidity is 27 and 29. Mass is the same almost, but here you can see center of rigidity is this is 27 and this is 30 because of this core wall. Then once it is removed, then that is taken care, and participating mass ratios. Is having torsion already in all the coupled with translation, right? And that's it for today's presentation. I hope it was useful. So do we have any Q&A?
Thank you so much, Vivek sir, for such a lovely presentation. There are some questions in the Q&A. You can take a look at them and you can answer some of them.
Okay. Okay. Was there some audio issues?
Yes, there was some
Initially?
audio lag, but it's because I think because of the Zoho platform is some issue, but we'll fix it in the next session. Again, thank you so much everyone for being so patient. Now, Vivek sir, you can take a look at the questions and answer them
Okay.
before yeah. Thank you so much.
There is a question, how to validate torsional results for semi-rigid diaphragm case wherein we do not get center of mass and rigidity. If it is about handling the torsional mode, initially you can start with the rigid diaphragm application to get the center of mass and rigidity. Later, you can, once the lateral resting system is reasonably fixed, then you can change it into semi-rigid diaphragm and continue the work and examine the model results. Torsional irregularity should be checked under static or dynamic loads. No, torsional irregularity can be checked for both. So when you're using for the response spectrum, then the method I was discussing by shifting the mass shall be used. Because in response spectrum analysis, the model during model combination, the signs are lost. So that will not be a useful result to check the end displacement to estimate the torsion irregularity. So static is better. If you are doing dynamic, then use that. Regarding the concept of shifting the mass using new load cases for response spectrum, which will be the load case we will be using for combinations and scaling. No, you will be using this as one of the combinations because you are considering now. So typically we use the response spectrum for the designing of members. We typically use response spectrum. Even if you wish, you can specify the specified ratio as a common eccentricity, and then you can proceed with the design. But when you are doing this, then you'll have to create combinations parallelly, one without any eccentricity and with positive eccentricity and negative eccentricity. So program will design for all three cases, and the critical one will be reported as we get in any number of load combinations. First mode and second mode, time period difference is less than 10% is okay or not okay. See, ideally, yeah, the 10% difference has to be maintained, but you can do this simply by introducing few more steps in creating that weaker and stronger translation. That is something in our hands. If 1.2 times delta average to delta max and the right mode, first mode, I mean, the first mode in torsion, can we proceed with the design? Certain times it becomes really impossible to deal with the torsion. Yeah, as per the code, we'll have to, some clarity is needed for the interpretation of the code, but I don't have an answer for this at this point of time. But typically, all the structures are subjected to this accidental torsion that is always designed, but it is exempted that I'm not very sure. Sorry about that. We need, there is a question that why we need a rigid diaphragm to calculate center of mass and rigidity. Center of mass is always calculated. The center of rigidity needs a rigid diaphragm. So we need a rigid body motion to calculate this distance, which is always perpendicular to that position of the element to the center of rigidity. So it has to be rigid. That's the reason we need rigid diaphragm. So with semi-rigid diaphragm, this in-plane deformations are allowed. So that is not possible. So the four-arm irregular building, a typical example building, an elevator in the y direction. How can those be considered as shear wall? There is no diaphragm connectivity to assume. No. So that's what I mentioned earlier. To start with, you start with the rigid diaphragm for the for addressing the torsional issues, and then to know the center of mass and rigidity. Without knowing that, you cannot address the issue. So start with the rigid diaphragm. Once reasonable behavior is obtained, then you work with the lateral resting systems, like the shear walls. That is the only way out. That is a question. Mode mode should be in X, Y, and torsion, or it can be Y, X torsion. The first two can be anything, X, Y, or Y, X. It doesn't matter. Torsion should be in the third. We have used only one diaphragm in all stories. It is okay. Yeah, it is okay as long as the mass or stiffness distribution doesn't change much. Typically, buildings will have similar framing, but small changes, but that's okay. But if it is significantly different, then you should use a different diaphragm in that case. Virtual work Okay, there is an output called energy or virtual work. Like you can utilize that can give some insight, but it is primarily the center of mass and rigidity which is causing this. You will have to bring them much closer as possible. The virtual work output can help you in identifying the frames that are has the largest comparatively with other members, how much work done in that member. That will also give use to some extent. Yeah, it is also possible. You can use that as a helper tool. I think some of the questions are repetitive. Unsymmetrical building with core on one side and just columns on the opposite. This is due to architectural constraints. Yeah. So architectural constraints is something challenging for everyone. I don't have an answer for that. You will have to. So what you can do is and strengthen the lateral resting walls on the perimeter, as discussed earlier. The core walls can be just an RCC wall, not a ductile or so that its effects are minimal. But the geometric stiffness will be there, but cannot be avoidable. But you can reduce its effect or the stiffness slightly to act as a gravity wall rather than a lateral resting system. You can try assigning some stiffness modifier for the shells for the walls F12 to a minimal value so that it will take very less lateral force. The other shear walls will come into play for resisting the lateral forces. So that is something you can try always. I think we're running out of time. Lakshay, I think we will answer other questions.
Yes, thank you so much for answering the question, Vik sir. I am posting the link for the Google form again on the Q&A section. You can upload all the questions there. We'll also copy the questions from the chat and add them to the FAQs, which we will be preparing right after the webinar. And we will share the presentation along with the link to the recorded session and the FAQs with you shortly in a day or two. Thank you so much, Vivek sir, and thank you so much everyone for being patient with this webinar. I hope to see you all again in the next one. Have a nice day. Thank you so much. Thank you, sir.
Thank you all. Thank you, Lakshay.
Thank you, sir.